Have you ever wondered how something super complex, like the sound wave from a trumpet, can be built from something incredibly simple? Well, today we're diving into the Fourier Sine Series. It's this amazing mathematical tool that let us construct really complicated functions just by adding up a bunch of simple sine waves. Seriously, it's a cornerstone of modern physics and engineering, and we're going to break it all down. So, here's our game plan. First, we'll tackle the big question. Why on earth would we only use sine waves? Then we'll get into the actual recipe, the formulas. After that, we're going to build a function that looks totally impossible to make with sines, see what that approximation actually looks like, and finally connect it all back to the real-world physics of sound. Let's get into it.
All right, first up, why just sines? I mean, you've got a whole universe of functions out there, so it seems kind of restrictive to just use one type, right? Well, it turns out there's a very specific, and I mean very physical reason for this choice.
The answer isn't really hiding in some abstract math textbook. It's all about the kinds of physical systems we're trying to describe. Just picture a guitar string. It's held down tight at both ends, right? It can't move at the top, and it can't move at the bridge. And that very specific physical setup, well, it has a perfect mathematical partner.
And this is the crucial point. We use a sine series for problems that have what are called Dirichlet conditions. Now, that's just a fancy term for a really simple idea. The function has to be zero at both ends. Think about it. A sine wave naturally starts at zero and ends its period at zero. It's the perfect building block for describing things like our guitar string that are fixed at both ends. They are a match made in heaven.
Okay, so now we know the why. Let's get our hands dirty with the how. This part is all about the recipe, the actual formulas we need to start building whatever function we want out of these sine wave Legos. So, this is our goal. This is the formula we're working towards. We want to represent our function, f of x, as this big infinite sum, that's what that sigma symbol means, of sine waves. Each sine wave in the series has a slightly different frequency, which is controlled by that little n, and a very specific strength or amplitude, which is given by that coefficient Bn. So, the big question is, how do we find that strength, that Bn? We use this integral formula right here. Now, I know it might look a little intimidating, but the idea behind it is actually beautiful. What we're doing is we're essentially asking our function, hey, how much of this specific sine wave are you made of? The integral isolates the exact amplitude we need for each and every single term in our series. It's like a mathematical prism, breaking our function down into its pure sine wave components. All right, enough theory, let's see this thing in action. We're going to try to build something that feels completely wrong for sine waves. A constant function, just f of x equals 1. This is basically a piece of a square wave. Can we really build a flat line just by adding up a bunch of curvy waves? Let's find out. We're just going to follow the recipe. Step 1, we plug our function, f of x equals 1, into that integral formula. Easy enough. Step 2, we do the integration. The integral of sine is negative cosine. Now, step 3 is where the magic happens. We evaluate this at our limits, 0 and pi. We end up with this little term here, 1 minus cos of n pi. Now, cos of n pi is pretty cool. It just flips between 1 when n is even and -1 when n is odd. So look at step 4. If n is an even number, that term becomes 1 minus 1, which is 0. The even terms completely vanish. But if n is an odd number, it's 1 minus -1, which is 2. So only the odd-numbered sine waves are going to show up in our final answer. And ta-da! Here it is. Our simple, flat, constant function is equal to this wild, infinite series. Notice two really important things here. First, just like we predicted, only the odd terms are left. Sine of x, sine of 3x, 5x, and so on. And second, look at their amplitudes. They get smaller and smaller, following a 1 over n pattern. The first term is the strongest, the next is only a third as strong, then a fifth, and it just keeps going. Okay, so we've done the math, but what does this thing actually look like? I mean, what happens when you try to force a bunch of perfectly smooth sine waves to make something with sharp corners, like a square wave? Well, you get a really fascinating and kind of weird little side effect. This is what's known as the Gibbs phenomenon. As you keep adding more and more sine waves to your series, the approximation gets better and better, mostly, except right at those sharp corners. The series will always overshoot the target value right at the jump. You get these little horns that never, ever fully go away, no matter how many terms you add. It's not a mistake. It's a beautiful, fundamental quirk of how infinite series work. So look, this whole process isn't just some abstract exercise for a math class. Every single term we just calculated for a square wave has a direct, tangible meaning in the real world, especially in the world of music and sound. Let's bring this full circle. Let's take that series we built for the square wave and connect it all the way back to that vibrating guitar string we talked about at the very beginning. What does our math actually represent physically? Well, if you could somehow pluck a guitar string into a perfectly flat shape, like our function, the sound it would make would be composed of these exact sine waves. Each value of n, 1, 3, 5, and so on, corresponds to a different harmonic or an overtone. The n equals 1 term, that's the fundamental pitch you hear. The n equals 3 term is a higher, quieter pitch. And our coefficient, that bn, tells you the volume of each of those harmonics. The fundamental is the loudest, and they get quieter and quieter, which is exactly what gives our square wave sound its unique character, its timbre.
So the huge takeaway here is that from the simplest building block you can imagine, the humble sine wave, we can construct this incredible universe of complex functions and signals. We saw it build a flat line, but this same method can build sawtooth waves, triangle waves. It can approximate almost any shape you can dream up, which really leaves us with a final question to chew on. What other impossible shapes are out there, just waiting to be built from these simple, elegant waves?